Hi, everybody. My name is Dominic, and today I'd like to talk about a study of methods for the generation of domain-aware word embeddings. This is joint work with my advisor, Cheng Jai. The motivation behind this work is that out-of-the-box word embeddings are usually trained on large-scale general-purpose corpora like Wikipedia. And since these are not specific for the application domain, they often perform poorly in these specialized domains. In addition to that is that application domains often have very small corpora, which makes training of embeddings difficult. And in turn, this leads to low quality embeddings. The research question that we are trying to answer in this work is how to best leverage general corpora like Wikipedia, which have a broad vocabulary but flat domain coverage, and domain corpora, which have a narrow vocabulary but deep domain coverage. So to answer our research question, there are multiple things we have to consider. For example, where is the combination of general and domain corpora are gonna occur in our method? So for example, it could be done at the corpus level by combining training data. It could be done at the model level where we try to change the model, or the vector level, where we basically take the already trained word vectors and try to manipulate them in certain ways. Since different models have already been heavily studied in previous research, we focus on model-independent solutions. In our experiments, we use the work tool VEC model, but in general, any word embedding model could be used instead. And we propose 2 vector and 1 corpus level method. The methodology that we use to combine domain-specific and general data can be broken up into 3 different approaches. The first approach is the interpolation of aligned embeddings. The second approach is the concatenation of embeddings. And the third approach is the weighted fusion of training data. I'm going to explain in more detail now what these 3 methods mean. First, I'd like to start with the interpolation of aligned embeddings, which we also call interpol. The idea there is that we do a weighted addition of the word vector spaces. So as you can see in this formula, the embedding space E smooth, which is going to be the resulting embeddings, is a linear combination of the domain word embeddings and the general word embeddings. We also introduce a mixing weight lambda, which basically accounts for how much general data will be introduced into the model. You can also think of this as a smoothing parameter, where lambda controls for the amount of smoothing that is used from the general embedding. However, the embedding spaces cannot simply be added because the embeddings have been trained on separate corpora, or even used separate embedding methods to embed them. Therefore, we have to do a transformation of one of the spaces so that it matches the other one. And this can be done by multiplying a matrix W with the domain embeddings, which should be equal to the general embeddings. W here is a transformation matrix that can be found using stochastic gradient descent, and this is the loss function for the gradient descent. Then we can incorporate W in the previous equation, such that we add the W here to transform the general embeddings into the same space as the domain embeddings, which then enables us to add them together. The next method I would like to present is the concatenation of embeddings, or concat. There we simply concatenate the word embedding vectors of the domain and general vectors into a single vector econcat, as seen here in this formula. The intuition here is that the model will learn to prioritize certain embedding dimensions using the training data. The third and final method I would like to discuss is the weighted fusion of training data, which we also call fusion. There we combine the general and domain corpora in a principled manner before training the embeddings. We control for the amount of domain data with a parameter n, which we also call the domain duplication factor. N specifies the number of duplications of the domain data. And there are 2 extreme scenarios. Either there's no domain data, which means n equals 0, or there's only domain data, which means n approaches infinity. Now I'd like to discuss our experiments and our experimental setup. The data set we use is called malware TextDB, which was proposed by Lim and others. And the goal is to classify relevant sentences for inferring malware actions and capabilities, which is, in our case, binary sentence classification, whether a sentence is relevant to malware or not. We randomly sampled the entire dataset into training, development, and testing. And we used 80% for training and 10% for development and testing. The performance on the dataset is measured in F1 score. The embedding algorithm we use is Word2Vec, which was introduced by Mikolov and others. And the classification network is a convolutional neural network introduced by Kim. We compare our methods to two baselines. The first one is general, which are embeddings trained on a large general purpose corpus. In our case, this is Wikipedia. The second baseline is domain, which are embeddings trained on a smaller domain corpus. We currently train our cybersecurity embeddings from a web crawl of security-related web pages. Hyperparameters that we investigate is the weighting parameter lambda in a range from 0 to 1 with increments of 0.1, the domain duplication factor n with no domain data or n equals zeros, or dominated by domain data n equals 100. The embedding dimensions we test are 100, 200, and 300. These are the results of comparing the different models with each other. We can see that Interpol performs best on both datasets overall, which is the underlined score in the table. Concat is often outperformed by just the domain baseline, where we just train embeddings on domain-specific data. Fusion is able to outperform other baselines under certain conditions, as can be seen for the 200 dimensions on the test set, n equals 50. However, training of the fusion method is very expensive because for each different setting of n, you have to retrain all embeddings. Domain performs better than general in the majority of the cases, which is expected because the general embeddings have general purpose data, whereas the domain-specific embeddings are trained only on domain data. Overall, we can see that combining domain and general data is generally beneficial because all methods that incorporate domain-specific information outperform the general baseline. We further investigate the setting of the lambda parameter, and in this plot we can see on the x-axis we have different settings for lambda, whereas on the y-axis we have different F1 scores, and we compare all the methods that we saw previously. Since the lambda parameter only influences the interpol method, you can see that the performance for all other methods is steady, whereas for the interpol, we see different values for each setting of lambda. We find that small amounts of general information can push the performance past other models pretty quickly. So even for 0.0, we already see it's performing better than all the other methods. Values higher than 0.5 actually hurt performance, as we can see that the information is steadily declining. An interesting part is that just transforming the general embeddings with the alignment matrix already boosts performance, as can be seen for the 1.0 case here. In addition to our quantitative studies, we also did a qualitative evaluation of the word vector space. We specifically focused on the word bug, which is ambiguous in different domains. For example, in the cybersecurity domain, a bug would usually refer to an error in a program. However, bug can also mean insects and has other meanings. In the table, we can see the closest neighbors to the word bug in different embedding spaces. As we can see from the table, the domain method mostly lists cybersecurity related terms, which is expected since it's only trained on domain-specific data. And in comparison, general captures mostly the biological meaning of bug. Using our interpolation method, we can introduce stage fright to the most similar words, and more general terms are ranked higher. For example, vulnerability and loophole. Finally, I would like to conclude with the following observations. Generally, combining the domain data and general data is beneficial. Interpolation performs best, and it should be preferred because of its flexibility using the lambda parameter. Concatenation is often outperformed, and the fusion model can achieve good performance, but it's costly to train. Consistently, we find that the general embeddings are the least effective in almost all settings, and the qualitative analysis indicates that we have actually a meaningful transformation of the vector space, and the interpolation method is used. Finally, I would like to thank you for your attention. If you would like to find out more about my research, please visit me at dominicsaylor.com.